So now we can begin. Sandeep, what we did in the last class? So we defined in the last class what are, so suppose we were given a linear operator t from v to v, and then we defined what is determinant of t and what is trace of t. So do you recall how we defined these two? So suppose you are given a linear operator, say you have p2x, say, or p2r. From p to r, you are sending. So here, what are the things here? Actually, you saw some examples already in the midsem, right? What was the example? p2r to p2r. What was the linear operator that was given? Differentiation. It was a polynomials of degree less than or equal to 2, and then you have d dx from here to here, a map, right? And then we were asked to write the matrix of this with respect to what? Exactly. So given a linear operator, if you are given a basis, you can write down the matrix of the linear operator. That is called the matrix representation of the linear operator. How do you do that? I mean, this was just for an example, but suppose you were given a linear operator T, a vector space V, and suppose B is a basis of this. Okay, so you are expressing the linear operator, the matrix of the linear operator T in terms of this basis B. How do you do that? Right. So you express T of B as a linear combination of the elements of B, and this A, the columns of A, is giving you that linear combinations, those linear combinations. Is it all right, Shotrik? Do you recall? Okay. So this is the matrix of the linear transformation, sorry, linear operator now with respect to this basis B, and we defined determinant of T as determinant of A and trace of T as the trace of A. The first question is that whether this is well defined. Well defined means that if you take another basis, does it change? Does the determinant or the matrix change? If yes, why it does? If no, why not? Right. We proved that if you take another basis B dash, then let A dash be the matrix of the linear operator T with respect to another basis B dash of V. Okay. Then what's the relation between this A dash and A? Yes, but even before that, how to write A dash? Yes, what is that P? Change of basis matrix, right? Yeah, right. Yeah. So if P is the matrix of change of basis, Shotrik again, how do you define that matrix of the change of basis? From B to B dash, you are going from B to B dash. So how do we define the matrix of change of basis from B to B dash? We require this to express A dash in terms of A. We would like to express the elements of the basis B dash in terms of the basis B. Okay, the new basis in terms of the basis B. Okay, so B dash, the elements of B dash, so you can consider it as V1 dash, V2 dash, Vn dash. Okay, you want to write each of these vectors in terms of as linear combinations of the old basis B. Okay, so some A1 V1 plus A2 V2 dot A and Vn. Okay, so you write the basis B here, and those linear combinations we were noting down as columns of some other matrix. Which matrix? This matrix P. Okay. So B dash is BP. This matrix is a matrix of change of basis. Okay. And then once you have this P, you can write A dash as P inverse A P. Okay. Now check whether the determinant and the trace of this are equal, that is A dash and A, whether they are equal. Take the determinant of A dash. Okay. So this is actually also for all the people who missed the previous class. Determinant of A dash is the determinant of this, okay, and you know that determinant is multiplicative, right? So that means this is determinant of P inverse determinant of A determinant of P. Well, determinant is a scalar, so you don't need, so in particular you know that the scalars are commutative, right? Scalar multiplication is commutative. So therefore you can club this and this together, determinant of P inverse and determinant of P, right? And if you do not immediately recall that one is the reciprocal of the other one, you can again use the multiplicative determinant and write this as determinant of P inverse P times determinant of A. And what is P inverse P? That is identity, right? So this is determinant of identity times determinant of A, and determinant of identity is 1. Okay. So this is just determinant of A. Okay. So these two determinants are the same, right? And then for trace, we saw that, you have seen this earlier, of course, that trace of AB is equal to trace of BA, and also in the last class we gave a quick proof of this. It's nothing but switching orders of summation. Okay. So this one, now you are going to use this fact, and you can take this as one of, so take this to replace this one, and take this one to replace this one. Okay. So you replace this with this, and what you get? You get that, so this one is the first one, this one is the second one. You take this one forward, and that means P inverse A, if you just write it there, P inverse A is trace of A, whereas on the left hand side you are getting trace of A dash. Okay. So from there we get that trace of A dash is equal to trace of A. Okay. And therefore you can take any basis and any representation of the linear operator in terms of, any basis and a representation of the linear operator in terms of that basis. Okay. Define the determinant to be the determinant of the linear operator T as the determinant of the matrix with respect to that basis, trace of the linear operator T as the trace of the matrix with respect to that basis, and these definitions are then, determinant of T and trace of T defined in this manner is quite well defined, because if you change the basis, this matrix changes by conjugation, which does not alter the determinant or the trace. Okay. Do you know what is adjoint of a matrix? Have you seen this? Okay. And do you know what happens, what is this one? A times adjoint, or you say adjugate of a matrix, whatever terminology you are familiar with. So what is that? Determinant of A, determinant of A to the power n minus 1, again this is a matrix, this is a matrix, so you don't get a scalar multiplying them. Identity, right. Okay. So that's the identity, and we are going to use it sometime later, but I just wanted to make sure that whether you have seen this earlier. You have seen this multiplicities, right? And then somebody asked what is a characteristic polynomial after finishing the class. So if you have this question, you should ask in the class just as it did, what is an adjugate matrix? That was very good. What's your name, by the way? Avinav. Okay, thank you, Avinav. So, Shautrik, characteristic polynomial of a matrix, suppose A is some n cross n matrix, right? We define its characteristic polynomial, say polynomial P A, suppose we define it as determinant of T I. Now, I is of the same dimension as this one, say I n minus A. Now, the first task for you is to see whether if we change A by conjugation, say A is changed to some P inverse AP, P is some invertible matrix, okay, does the characteristic polynomial change? Let us figure it out. Call this one as A dash, okay. Okay. So, what we need to do here, we want TIN minus P inverse AP here, right, okay. And this one is determinant of, well, note that IN is just P inverse P, right. So, you can take P inverse from on the left out and P from here out. So, I am going to write it down here, P inverse P minus, or you can also write as P inverse TIN P minus P inverse AP. Okay. Then what are you going to do? You want to take P inverse out from here, P out from there, okay, on the right. Okay. So, then P A dash T, this is determinant of P times determinant of Ti minus A times determinant of P inverse, right, sorry, determinant of P inverse, determinant of Ti minus A times determinant of P. Again you can club these two together, right. So, what do you get? This is determinant of Ti minus A, which is equal to P A T. Okay. Exactly. The characteristic polynomial of two similar matrices are the same, and therefore, all the eigenvalues occur with the equal multiplicities in I mean for both of these polynomials, because the polynomials are the same, right. So, again a question for you, since we were not there in the previous class. Suppose now you are just given the equality of these two things, that is characteristic polynomial of A dash and the characteristic polynomial of A, they are equal. Can you tell that A dash and A whether these two are conjugate or not? Whether I mean we saw that if A dash and A are conjugate, that is they are similar, then their characteristic polynomials are the same, must be the same. Okay. Now, the question is that if A dash and A have the same characteristic polynomial, whether they are conjugate of each other, whether they are similar. So, this is the question. If P A T is equal to P dash, no sorry, P A dash T, then R A and A prime necessarily similar. So, this is the question. You are given the equality of the characteristic polynomial, the question is that whether the matrices should be similar. Yes, but let him answer. Yeah, please. Yes, same characteristic polynomial. Can you give a small example, or just give the idea? I mean, how you can construct two matrices which may not be similar, but which have the same characteristic polynomial. It may not be an explicit example, but what is the idea that you should proceed with? Well, if these two are equal, what does it mean? Their eigenvalues are the same, right? Now, if you're given a set of eigenvalues, suppose all the eigenvalues of a matrix, can you write down two, at least two matrices which have the same eigenvalues? Just two distinct matrices with the same eigenvalues. Say lambda 1 and lambda 2 are two eigenvalues, okay? Then just a 2 cross 2 matrix. The easiest one? Yeah. Very good, the diagonal matrix, okay? So lambda 1, lambda 2. And another one? Yeah? Yeah, of course, one can switch it, okay? So lambda 2, lambda 1, and that's also a good thing. So now what you are asking is that whether this and this are what you call the similar, okay? So take for an example, say 0, 0, 0, 1, and this one as 1, 0, 0, 0. Let's explore whether these two are similar, okay? If they're not, then you have already got your counter example, right? Okay, so if this and this would have been similar, then suppose P is equal to A, B, C, D. Okay, so we would have that 0, 0, 0, 1 is equal to well, P inverse. Call this A dash, maybe call this A. And suppose this is equal to P inverse AP, okay? Then this would mean that this is P times this one, PA dash is equal to AP, right? So that would mean PA dash is ABCD times that one, 0, 0, 0, 1. This is going to be equal to A was this one, 1, 0, 0, 1 times A, B, C, D, okay? So that would imply that this one is, yeah? Wait a minute. A is 1, 0, 0. Thank you. Yes. Yes, of course. So this one is giving you 0, 0 here, right? Of course. And this one is giving you B and D, okay? And that is equal to, now what is this? 1, 0. So this is giving you A and B, okay? And 0, 0 here, right? So we'll have this equality. And that would mean, well, B is equal to B, A should be equal to 0, and D should be equal to 0, right? All right, is it? It's fine, right? So that would mean that A equal to D, and both A and D are 0, right? Now, can this happen? A and D both 0, whereas this is just BC. Well, this is not going to give you a contradiction immediately, because B and C could be something else, right? Ah, that's right. Of course, yes, indeed, yeah. So these two are similar. So this is not giving you the counterexample immediately. Okay. So that was a. I mean, did you all understand what he just mentioned? That is, we need not go. I mean, we need not do this computation explicitly, because this was lambda 1, lambda 2. This is suppose we are having a linear operator. So this is and well, actually we have not yet discussed what is a eigenbasis, but suppose this is a matrix of a linear operator with respect to the standard basis. Okay. Now, if you switch the basis, this is going to be the matrix of the linear operator with respect to the other basis. Okay. And going from one basis to another, that is just switching the elements, is, well, this is this matrix 0 1 1 0. Okay. That will be the matrix of the change of basis, right? So with that you are operating on this P inverse AP. Okay. And that is giving you, I mean, that is giving you this one from this one by conjugation. Okay. So these two are indeed similar. Thank you. And now you have to construct something else then. Yes, Trishit? A and D, okay, look here. Here A is 0, D is 0. Isn't this matrix invertible? Well, check its determinant. Determinant is -1. So it must be invertible, right? And you can in fact write down its inverse easily, right? This is just what? Can you tell me what is the inverse of this? -1 in place of 1. Okay. And just that, is it the same matrix? Is the same, because here you have to divide by the 1 by the determinant of this matrix, and that is -1, right? So you are multiplying with -1 here, and it's the same matrix, right? It's inverse. Okay. Right, Rishit? All right, because you forward that 1 by the determinant outside. Okay. So indeed this is invertible. Okay. Even if both A and D are 0, you will have, I mean, if you have the entire row or the entire column 0, then you can say that the matrix is non-invertible, but not in this case. Okay. All right. So yeah. So this one, though, I mean, it was a good attempt, but this doesn't work. So let's keep this ordered here. What else can you do? Yes. No, but he has missed the last class, so he's just trying to construct one. Please. So note that this, how do you define the determinant of a, I mean, how do you define the characteristic polynomial? It is determinant of Ti minus A, right? Now, if in particular this is a diagonal matrix, this Ti minus A only have the diagonal elements T minus lambda 1, T minus lambda 2, dot T minus lambda n, right? Now, in particular, again, if this is a lower triangular or an upper triangular matrix, what will happen? Again, you are getting T minus lambda 1 or T minus lambda 2 here, okay? And you know how to compute the determinant of a lower triangular or upper triangular matrix. It's again the product of the diagonal entries, right? Okay. So that will mean that this matrix and this matrix will have the same eigenvalues. Okay. And now, in particular, if you choose the eigenvalues to be rather simple ones, so say for example, if you choose both of these to be 1s, then it's quite easy to see that this is not a conjugate of this, because whatever conjugate of this you can imagine, all are going to give you just the identity matrix. P inverse IP is I, right? And this is not I. Okay. So these two are not conjugate. Okay. Though their characteristic polynomials are the same. All right. Now, where should we go? last class we defined what is algebraic multiplicity, right? Let's define what is geometric multiplicity of an eigenvalue. Okay. By the way, why are we interested in eigenvalue analysis at all? I mean, a linear operator and its eigenvalues, because you see its application nowadays, face recognition, speech recognition, even when you search some topic on the internet, it's an algorithm used by Google called Google's PageRank, and underlying things all are, I mean, this linear operators from some space to some other space. And in particular, if you Google for these concepts, eigenface or eigenvoice, okay, you are going to get something. This is related with face recognition, this is related with speech recognition. Okay, so this is actually a space of faces, that is, you have like say black and white pictures of 1,000 of faces, and each pixel represents some coordinate, and then its brightness is the value of the coordinate, say. Okay, and so you have some say 256 cross 256 matrix, I mean the space, and the values have a certain range, and then you define the space of such matrices to be the space of, I mean the underlying space of eigenfaces. Just remember to Google for this, just to give you some motivation. Okay, and remember, even here when you Google, you are using eigenvalues and eigenvectors. Okay. Okay, so we are not going to show you exactly how you do this, how do you do the face recognition or how do you do the speech recognition, but we are going to give you the tools with which you do this. Okay. Yes. By eigenface, we mean some kind of a eigenvector on the space of parameters of human faces, which are captured in that set of pictures. Okay. So eigenfaces are eigenvectors in that space. Eigenvoices are eigenvectors in the space of voices. Okay. And then with that, with an eigenbasis in that space, one is representing one's. So you recall, every vector in a space has a unique representation in terms of a basis, right? So if you have a basis of the face of spaces, I mean, if you have a basis made of eigenfaces, you can represent your face uniquely in terms of those. If you have a basis made of eigenvoices, you can represent your voice uniquely as a linear combination of those. Okay. All right, now what is called diagonalization. Okay. Or let's say what is diagonal, I mean what we mean by a diagonalizable linear operator. Okay. The definition is rather simple: diagonalizable linear operator. What is that? So suppose T from V to V is a linear operator. Okay. And then you have a basis B, okay, such that the matrix of this basis B, when you write it down, this A is a diagonal matrix. Okay. So you have some basis B in terms of which the matrix of this linear operator is diagonal. Okay. Then we call T to be diagonalizable. Okay. So let's see what properties such a basis should have. Okay. suppose V is such a basis V1 to Vn, okay, and then suppose T of B is B times some diagonal matrix, call it A1, A2 dot 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 An, okay, 0 everywhere else. Okay. Then write it out clearly. This is V1 dot 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 Vn equal to V1 dot dot Vn times this diagonal matrix, right? A1 dot 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 An, 0 here, 0 here. Okay. Sorry, this is T of this. Excuse me. Not just V1, V2 to Vn. That doesn't make sense. Excuse me. So this is T times this. Okay. So that means T of Vi is equal to Anubhav. What is that? T of Vi. So if you have T of V1 to Vn as V1 to Vn times this diagonal matrix, what will be T of Vi? Yes? Wonderful. So what can you say about this Vi then? Right, it's an eigenvector of the linear operator T, right, with eigenvalue Ai. Okay. Why this is an, again, why this is an eigenvector? What other condition except this equation do you require? Anubhav? Wonderful. It's a part of the basis. That means it's a so if you just take Vi, it's a linearly independent set. I mean the singleton set. Okay. That in particular means that Vi is not equal to 0. Right. All right. So if you have a basis with respect to which the matrix of linear transformation is diagonal, that basis is going to be, all the elements in that basis are going to be eigenvectors. Okay. So now we can define what we mean by an eigenbasis, which is underlying these two things. An eigenbasis is a basis of a linear operator T from V to V made up of eigenvectors of T. Okay. So the question is then whether such an eigenbasis exists always. Can you give an example? I saw that some of you nodded. Nodded in a dismissive way. So that means that you know that this may not always exist. Yes. Right. Yes. Right. Wonderful. Yes. Thank you, Snowmi. So in particular, define this, so this is an example. Define T from R2 to R2 by this, that T of AB is equal to this matrix which we just saw, 1 1 1 0 times AB. In other words, T of AB, would you see this? Maybe we write it on this side. So define T of AB to be A plus B and B. Okay. Let this be the linear operator. Okay. Then we just saw that this matrix is not diagonalizable, right? So in particular, this linear operator will not have a basis made up of eigenvectors. Okay. This is an example of a linear operator which is not diagonalizable. Okay. Now, the concepts of algebraic and geometric multiplicities, one of which we have already seen, it is algebraic multiplicity, and one of which we are just going to see, that is geometric multiplicity, will connect to this concept of diagonalizability of a linear operator. Okay. So, now we define what is geometric multiplicity. Of an eigenvalue of a linear operator. Okay. Kaushik? Yes. So, please be attentive to the board because we are going to define a new concept. Okay. Deepto, you have any doubts? Oh, okay. So, we just saw about this example, right? That is okay. So, suppose at first, suppose you are considering some eigenvalue, say lambda of a linear operator t. So, there exists some v which is not equal to 0 such that tv is equal to lambda v. Okay. And that would mean that if now by I we denote the identity operator on v, that is which is sending just v to v itself, okay, small v to small v. If by E we denote the identity operator, that is I of v is equal to v, then this equation now we are going to write in terms of t and this I. Okay. Then we have t of v is equal to lambda I v, right. That means t minus lambda I v is equal to 0. What we are doing? We are now defining a linear combination of linear operators. Okay, that is something that we can still do, right? If t1 and t2 are linear operators from v to v, then we can of course define a t1 plus b t2 to be again a linear operator from v to v. Just this one would map, wait a minute, a t1 plus b t2 of v, this will just be a t1 v plus b t2 v. This is a definition of linear combination of linear operators. Okay, it's quite intuitive, right? And so this tv equal to lambda I v, we can write it as t minus lambda I of v, which is equal to 0. Okay, so this is another linear operator which is having a non-trivial kernel. Okay, I am just going to wipe these two parts here, okay, or maybe just the next line. Okay. So we just considered there the kernel of t minus lambda I, and what we can say? What we can say about its dimension? Greater than equal to 1, because there exists at least one element which is not equal to 0, that is the eigenvector of t with respect to this eigenvalue lambda, okay, corresponding to this eigenvalue lambda. Okay. Now, we define the geometric multiplicity of lambda to be equal to the dimension of the kernel of this operator t minus lambda I. Okay. We know that kernel of Ti is non-trivial, so dimension is at least 1, but here what we mean is that if you take an eigenbasis of made up of just the eigenvalues, not eigenbases actually, a set of linearly independent, the maximal set of linearly independent vectors which have eigenvalue lambda, which are correspond to eigenvalue lambda, that is going to give you a basis for the kernel of this. Okay. Just a small example maybe that would be perhaps helpful. So, consider this matrix 1 1 0 0, left multiplication with this identity matrix. Okay. What are its eigenvalues? 1, right, and so then t minus lambda I is null matrix, right. So, its kernel is in particular what? The entire R2 or whatever field you are talking about. So, F2 say. Okay. So, the whole field is its kernel. In particular, you can take any two linearly independent vectors in R2 and that would form a basis of the kernel, okay, and the dimension of that kernel would be then 2. All right. Gayatri, is that all right with you? It's not? Okay. So, again, so suppose T is left multiplication by this. Okay. We have to leave now, but just after this. Okay. Class? Okay. So, left multiplication by this is T. Okay. So, T minus lambda I, now lambda is just 1, okay, and then T minus lambda I is the 0 matrix, right, because lambda is 1. So, these are the eigenvalues. In particular, this matrix has only one eigenvalue, that is 1. Okay. So, this T minus lambda is just going to be the linear operator which is sending everything to 0. Okay. Well, the matrix of T with respect to the standard basis is this one, okay, and then lambda is 1, I is again this one 1 1 0 0, right. So, this is your matrix of T minus lambda I, okay, and therefore, so this is the matrix of T minus lambda I, okay, is equal to this, which is the null matrix, right. And so, the entire R2, entire space R2 or F2, whatever you call it, is a kernel of this, is inside the kernel of this map. So, the entire space is itself a kernel of this map, right. And therefore, you can choose any two linearly independent vectors in R2, okay, and that would give you a basis of this space, kernel of T minus lambda I, okay, the null space of this operator. Not, you don't call null, you call the kernel of this operator, or if you think of matrix, then it's a null space of this matrix. Okay. And the dimension of this, in particular, that is actually the nullity of this matrix, and the nullity of this matrix is the entire space. Okay. Not nullity of this matrix is the entire space. The nullity of this matrix is the dimension of the entire space. Okay. And dimension of the entire space is 2. So, the geometric multiplicity of 1 in particular here is 2, okay, and what it is its algebraic multiplicity 2 again, right, because its characteristic polynomial is T minus 1 whole squared, right. So, 1 is appearing twice as if you just consider it as a root of this, okay. So, that means its geometric and algebraic multiplicities are equal, are the same. We'll see that this is in general true if the geometric and the algebraic multiplicities of eigenvalues are equal, then the operator is going to be diagonalizable. Okay. This is actually an if and only if condition. Okay. Otherwise, one of them is always going to be greater than the other. One, a fixed one. Which one? Can you guess? How do you guess it? I guess you have seen in the first semester this inequality, right? Did it help? Well, it's completely unrelated. Right, but you have the abbreviation same. So that's all for today's class.